So we're going to talk about section 1.2 today. This is our first look at one of our big tools of calculus, which is limits. Limits are sort of the nuts and bolts behind our two big ideas. So this one we're looking at limits graphically and numerically. And we're going to talk about the definition. We actually do not get into the strict definition, but we want an intuitive understanding of what a limit is going to work for us. Okay. So I have some things displayed here. You can go ahead and put this in your calculator and explore with us. Basically everything I have up here I generated using my TI graphing calculator. So I'm looking at the function sine x over x. Now always in this class when we deal with trig stuff, make sure you're in radian mode, not degree mode. Okay, so I started off with this sine x over x, and I graphed it using a window -5 to 5, -2 to 2. Now, one thing that you'll see when you graph this is, when you actually graph this, it looks like, if you look at the graph, in most of the graphing calculators, it doesn't look like it has a hole there. It actually looks continuous. We know it's not continuous, and the reason why we know it's not continuous is if we plug 0 into this, we get 0 in the denominator, which of course is not possible. So if I ever have a situation like that where I look at my graph on my calculator and it looks continuous, but I know it's not, that has to be a hole. The TIs are sort of limited in their ability to show you that. If you do trace with the newer calculators, it will show you a gap there, but most of the calculators, you're just not going to see it. So just once again, if you see a graph that looks continuous, but you know that it doesn't have a value, that's going to be a hole. And then of course, this is why we back it up using the table, because the table is going to give us that information. So on the table I set up here, if you want to go to your table, set the start to be -0.5, and then your delta table, your change in the table will be 0.1, and you'll get these values here that I'm displaying to 4 decimals. Now what we're going to use is, we're going to use this function sine x over x to start discussing what it is to find a limit. Okay? So we're looking at, basically everything we're doing today is not algebraic. We're looking at things both graphically and numerically. Now basically what a limit is if I look at what it's approaching on both sides of the value. So here we're going to approach 0. So as I approach 0 from the left, what does it appear to be approaching? And as I approach 0 from the right, what does it appear to be approaching? And that's basically the idea. Now, if you look here, as we move from the left, we have values like 0.95, 0.97, 0.98, 0.99, 0.99. It seems that from this direction, we're approaching 1. Also, the exact same thing from the other direction, we're approaching 1, which is very important that we're seeing it from both sides. So we look at from both sides, or whatever that x value is. Same thing graphically. If I approach from the left, the output appears to be approaching 1. From the right, it appears to be approaching 1. If these two values agree, then that's our limit. So our limit here is going to be 1. So if I ask you the limit as x goes to 0 of sine x over x, that's equal to 1, because from the both sides it's approaching 1. Now, the definition is a little bit trickier in that. For the most part in this class, that's the way we're going to look at limits. If we look from both sides of whatever that x value is, if it's approaching the same value, then that is the limit. We'll look at some situations if it doesn't approach the same value on both sides. The thing we want to understand is the actual definition is a little bit trickier. They use what are called delta epsilon proofs. And intuitively what it means is if I say the limit here is 1, what I'm saying is I can get you to as close as 1 as possible. You tell me how close. So let's say we say that 0.9983 isn't close enough. What if we want it 0.999? Now we might not ever get exactly 1. Can we get here? And basically the delta epsilon proofs are basically playing this game. And numerically I want you to understand is if we say the limit's 1, we can get as close to 1 as we want. So if you say 0.999, there's going to be a value. So I did a little bit of experimenting. I think I tried with something like f of 0.09, right? And that gave me, so I'm basically just looking just to the left of this. I get 0.9986, not quite there. So f of 0.08, that gives us 0.9989, close, very, very close to this, but not quite there. And of course, I go 0.07, and we get 0.9991. So yes, we're as close. And basically, if we say a limit's equal a value, we can play that game with any point. Like if I said, I want to know when the output is 0.999999, you're going to be able to find an x that equals that. And that is what we mean by a limit, okay? So let's sort of define it within the scope of this class, as it has to approach the same value. As we approach the x value from both sides, the output is the same from both sides. Basically what I have up here is the definition that will serve us well in this class. This is not the strict definition. The strict definition of limits is quite tricky and beyond the scope of this class. Okay, so if I say the limit as x approaches c of f of x is equal to L, L being some whole number, okay, or not whole number, but real number, what I'm saying is as x approaches c from both sides of x equals c, f of x gets closer and closer to L, okay, on both sides. And then this little bit kind of ties into the actual definition, which is important to sort of understand intuitively. F of x can get as close to L as we choose for some x value on both sides. Not necessarily equal to L, but as close as we may choose to L. So if we want to be just 0.0001 off, 0.00001 off, we can get there. Okay, so if I'm looking at this graphically, if this is C, and this is my f of x, okay, and that would be our L. Okay, maybe it's missing, maybe it's not, maybe it's continuous, maybe it actually gets to L. But the idea with the limit is it can get as close as we want, and that's on both sides. And that's going to work as our definition. Okay, let's now look at a situation where the limit doesn't exist. So if we look at this graphically, this kind of gives us an interesting graph. Realize, and if you looked at a table, you would see this. If I plug in values that are positive here, I'm going to end up with positive value over the same positive value. So it doesn't matter what I enter into x, both being positive, I'm going to get 1. Okay? So what I get for all those positive values is the constant function 1. All right? Now what happens on the left side is that I'm plugging in the same values top and bottom, but the top will be positive, the bottom will be negative. So we're going to get 1, but we're going to get negative 1. So this graph looks like this. You can also express this as a piecewise function. Oop, I did that backwards. So that'll be negative 1. So let me just say that with this particular graph, if you do graph this, your graphing calculator, once again, is not going to give us sort of this look that we're clear this is holes. It's very important to show this. At x equals 0, this thing doesn't exist. So this is an example of a limit that doesn't exist. So as I said before, if a limit exists, or if a limit's equal to a number, it means that it's approaching from the same value from both sides. So notice as we approach 0 from the right, our output is approaching 1. In fact, it's 1 the entire time. And as we approach from the left, that's negative 1. If these do not agree, then we would say the limit does not exist. Okay, I just use D, N, E. Just some notation that actually isn't being introduced in this section, but I think it's sort of important to sort of start thinking about this. Some notation to say the limit as x approaches from the left looks like this. You put the number there, and it's almost like in the exponent spot. So just a little bit up to the right. That means from the left. So from the left of absolute value of x over x is equal to negative 1, which does not equal 1, which is equal to the limit as x approaches 0, and that's from the right. Same thing, but with a plus from the right. And we'll do more with that notation in the coming sections here. And that's absolute value of x over x. So in order for the limit to exist, those two things have to agree. Okay, let's look at two more examples here. We are going to be looking at two situations where we're looking at vertical asymptotes. Vertical asymptotes tend to be pretty easy in this context. So this particular one, we have the standard 1 over x shifted over 3 to the left. I get something that looks like this. This one's pretty clear to see. Okay. So once again, what is this thing approaching from the right? Well, it's not approaching a particular number, it's approaching infinity. From the left, it's approaching negative infinity. So once again, using that notation I talked about before, the limit as x approaches 3 from the right of 1 over x minus 3, we would say is infinity. The limit as x approaches 3 from the left of 1 over x minus 3 is equal to negative infinity. So these obviously don't agree. In fact, they disagree very badly. So we would say that our limit here does not exist once again. These values have to agree. Now, here's the deal. This one is sort of different in that context because this graph looks like this. From the left, it approaches infinity. From the right, it approaches infinity. So when we talk about L at the top of this video, L is a value. It's not infinity. Infinity is not a value. So this does not exist either because when we say the limit as x approaches c of f of x is equal to L, we're saying that equals a value. Infinity is not a value, so that doesn't exist. Down the line, we will define infinite limits in a different context. At that point, some people might say that this is actually equal to infinity because it agrees. Here, definitely does not exist. Negative infinity on one side, infinity over on the other side. This one, if someone does say infinity down the line, in the context of infinite limits, you know, we would let that slide. But in the context of talking about just L being a value, that does not exist. All right, let's look at one more graphical example, and that will do it. Okay, last example for the video. This one's purely graphical. You probably want to get this down in your notes. This is kind of a complex looking graph. Something I could definitely define from a piecewise function expression, but we don't really need to. This is just used to make a point, okay? One of the things I also have to talk about before I get into this example is very, very important when I talk about a limit. It's what it's approaching, and what we sort of concern ourselves with the limit is what we're approaching, with the functions approaching on both sides, not of whether or not it gets there. Sometimes it will get there in a case where we would say the function's continuous, but a lot of times not, because the whole point of limits is it allows us to evaluate what we wouldn't normally be able to evaluate. So we use them a lot when actual value is undefined at that point. So it's very, very important when we talk about limits, you remind yourself that it doesn't actually get there. So it doesn't matter whether it gets there or not. So for instance, here you can see there's no value there, or here there is, and that's the whole point of this exercise. So let's go through this. The limit as x approaches 2 of f of x. So as we approach 2 from both sides, what are we approaching? So you can see from the right of 2, we're approaching 1, and from the left of 2, we're approaching 1. So the limit is 1. Doesn't matter that we don't get there, okay? Now, what is f of 2? Well, f of 2 simply doesn't exist. It does not exist. But that has no bearing on the limit, okay? The limit as x approaches 1. Now, limit as x approaches 1 is a little different. So from the left, it approaches 2. From the right, it approaches 2. But it also gets there. That's equals 2. And this is what we call a continuous function, which we'll define in more analytical terms later. So here we see that it does agree, but it doesn't have to. Okay, limit as x approaches negative 1. So from the left, we see that this approaches negative 2. From the right, it approaches 1. Those do not agree, So this does not exist. Now, f of negative 1, notice there's a value hanging up here, actually has a value. So that is 4. The fact it has a value has no bearing on what that limit is. Okay? Limit as x approaches negative 2 of f of x. So from the left, we're approaching 2. From the right, we're approaching 2. Excuse me, negative 2. So that is negative 2. And then finally, f of negative 2, once again, doesn't exist. So the whole point of this is sort of outlining that point that sometimes the value doesn't exist, sometimes it does, but the limit itself, it doesn't matter what actually happens at that point, it's what it is approaching on both sides. So that is 1.2, finding limits graphically and numerically.